Today I would like to talk to you about a new function of PowerFactory 2019, the Co-Simulation tool. With this Co-Simulation tool, you can time simulate one network model in either the RMS or EMT domain or with a combination of the two. This network model can be split such that processing is done across multiple cores, in parallel with other software, or in parallel with another instance of PowerFactory on another computer. To begin with, we will initialize our co-simulation. Firstly, you click on the drop-down arrow and select Simulation RMS-EMT. Find the icon with two stopwatches next to each other. Here you can select the co-simulation type, single domain, multiple domain, or co-simulation with an external solver. Here you can select your simulation method, implicit or explicit. Implicit gives exact results, however, it has certain requirements for boundary modeling, which I will explain to you later. Here, you can also define the synchronization period, start time, and where the results will be saved. Under the tab Single Multiple Domain, we can define our regions. Here, one region has already been defined. Region 1 is defined by boundary 1 and is an unbalanced RMS simulation. To create another region, right-click and select Append Rows. Right-click under Defining Boundaries and select Select Element Type. Already available to me is a predefined Boundary 2, which shall be used to define Region 2. Next, I will select the initial conditions. Available to me already is the initial conditions for Region 1, which is for an unbalanced RMS simulation. Since we want to simulate Region 2 in the EMT domain, I will click the New Object button and a Calculation of Initial Conditions object is automatically created. For my initialization, I will choose instantaneous values and a step size of 0.1 milliseconds. Once the simulation has been defined with the settings you require, you can click Close and OK. Now we have Region 1 simulated with an RMS unbalanced simulation and Region 2 simulated in the EMT domain. Next, we have transformation settings. Here we can define the transformation along boundaries where an EMT simulation meets an RMS simulation or a balanced RMS simulation meets an unbalanced RMS simulation. Here you can define values such as maximum allowed unbalance factor, maximum allowed total harmonic distortion, or your FFT window. You can set different transformation settings for different regions or boundary lines, or have the same transformation settings applied to all regions. In the Advanced tab, you can find additional settings as well as your parallel computation settings. Here, I can see that my computer has 4 cores available, which means that I can have a maximum of 4 separate regions. As I showed you earlier, we have 2 regions. Region 1 will be simulated in the RMS domain and Region 2 in the EMT domain. Boundary objects are used to define our regions and must be defined along a line object. All lines that are used to define boundaries must have 2 regions overlapping them. As you can see here, between Region 1 and Region 2, we have 2 boundary lines. If you click on the Network Model Manager, select Boundary and double-click on Boundary 1, you can see the lines that define this boundary. Selecting Mark Interior Region highlights all the elements contained within the region. Here you can see that the interior region of Boundary 1 includes these 2 boundary lines. Further, when you mark the interior region of Boundary 2, you can see that these 2 lines are included in Region 2 as well. If, for example, you want to create a third boundary along this line here, all you have to do is say that this cubicle is part of Region 2 and that this cubicle here is part of Region 3. One way to do this is to right-click on this cubicle and select Define Boundary. I'll create a new boundary called Boundary 3. When I mark the interior region, I can see that it includes the boundary line and the bus bars and generators connected. Now we need to edit Boundary 2. To do this, right-click this cubicle here and select Add to Boundary. Marking the interior region of Boundary 2, we can see that it now does not include Region 3 except for the boundary line. I'm going to undo the changes that I've just made now so that I can simulate with just the original 2 regions. Boundary lines must be modeled as a type L line or modeled as a line which is part of a line coupling. For implicit simulations, boundary lines must be long enough to account for transmission delays, and they must be modeled with distributed parameters. For explicit simulations, only the general requirements about your type need to be met. By clicking on simulation events, we can see that there are 2 short-circuit events in this simulation. A 3-phase fault is applied to a bus bar in region 2 at 1 second and is cleared at 1.1 seconds. To simulate, firstly we initialize the co-simulation. Once initialization is complete, we can run the simulation. So here are the resultant waveforms of our simulation. What we have is voltage A at boundary 1 and at boundary 2. That's voltage phase A. So we have in red, we have the phase A voltage for when we do an RMS to EMT co-simulation. In blue, we have our voltage when we do an EMT to EMT co-simulation. And in green, we have our phase A voltage when we just do a EMT sequential simulation. So by doing this, we're able to compare the different results that we get for different types of co-simulations, and that helps us understand what kind of information we can expect from these different types of simulation. So over here at phase A, boundary 1, we have our RMS to EMT co-simulation waveform is actually in the RMS domain, while here we can see it's in the EMT domain. By the looks of it, it seems in both waveforms, our blue and our green match up exactly. So because we're in the, we did an implicit simulation, it seems that our EMT sequential simulation and our EMT to EMT co-simulation give us what could basically be considered the exact same result. There are some minor differences between our RMS to EMT co-simulation and our EMT sequential simulation, but there are also quite striking similarities. So if the implicit method of calculation is considered exact, why don't our results match up entirely? Well, we could expect that there would be a natural loss of information when simulating an RMS instead of EMT. Doing a fast Fourier transform of the results, with the fundamental frequency set to 1 Hz, we see that the 60 Hz component of the 3 sets of results match exactly. This case is quite interesting since the extra harmonics in the sequential simulation seem to be lower than 60 Hz. We have a 40 Hz component in the fast Fourier transform, and looking at the waveform, there does seem to be a lower interharmonic present. Doing an unbalanced frequency scan at the bus bar in question, we see that there is a large resonant peak at the 0.658 harmonic order. This equals to about 39.5 Hz. In this example, I have shown you the voltage and current waveforms at the boundary lines. Minor differences from the purely EMT simulation are observed, but these can be explained. However, normally, we are not so interested in the behavior at the region boundary, but more in what happens inside the EMT region. Within the region, we can expect the RMS to EMT responses to have an even higher correlation with EMT to EMT responses.